Good day, everyone, and I am back to talk with you all about the second half of the construction surveying handout that I had given you on horizontal curves. And we are going to work through some of those problems now. Actually, in particular, we're going to work items F through J. If you remember in my last video series, we had left off at we went to items A through E, and we're about ready to pick up items F through J. I'm going to begin by sharing the screen with you again, and we'll start out by looking at the assignment again, and then I'll bring in the whiteboard, and we'll be discussing a little bit, and I'll try to sketch, and again apologizing for my very crude sketches, but we can use the sketch to talk a little bit about what it is we're doing here today. Again, this is the fourth page in the series of this PowerPoint handout that I had given you guys, and this one here talks about some of the curve information and how to solve a typical horizontal curve. So I am going to go into the screen for that, and again talk to you guys about what we've done to this stage in the game. So just to recap where we've been, remember we actually have this project that we started. We know we have a tangent coming in and a tangent going out, meaning a straight line going in, a straight line going out. It's the design engineer's objective to calculate or to compute a horizontal curve, which will allow us to transition from one horizontal tangent to another horizontal, or to one straight tangent. So we're going to be able to do that. We know that based upon the information for horizontal curves, that we must have at least two pieces of horizontal curve data to make it unique. In this situation, we were given the radius and the deflection angle, or central angle right here, or the intersection angle has been called in different publications. So all of that being said, we do have two pieces of information. Additionally, we have information about the station of the PI. Remember that I'm going to come back to this point right here. The PI is the point at which, the point of intersection in which these two lines would intersect. So basically what we had done in our first 5 pieces of information is we went through and we used the formulas written over here on the side to first of all calculate. The first one, item A, was to calculate 1/2 of this angle right here, and that was simply done here. Again, bearing in mind, remember the information for our angle is given to us in degrees, minutes, and seconds. So we will have to be either dividing in degrees, minutes, and seconds, or converting those numbers to decimal degrees and then dividing that out. We are also asked to calculate the tangent. The tangent is this distance right here, which is the distance from the PI station back to the PC station. Also, we were asked to calculate the length of the curve. The length of the curve is the distance from the PC to the PT, and that happens along the curvature line, or the design curvature line. These formulas were given over here on the side, but I also gave you in a handout some of the typical formulas used in this process for your information and for your reference. We were asked then at letter D here to calculate the PC station. The PC station is the point at which the curve begins along the tangent. So we calculate the PT station by taking the PI station, subtracting the tangent distance to get back to the point. We did that, and we calculated by subtracting this tangent distance. That tangent distance was 218.90. Therefore, our PT station was station 14 plus 7560. So that's 14 plus 75.60. That becomes the station of this. We were then asked, excuse me, to calculate the PT station. The PT station would be this point right here, which is the point along the tangent going out at which the curve would end, and that's where we would come into our next tangent right here. So in calculating the PT station, the formula for calculating the PT station requires that we find the station of the PC, and what we do is we add the length of the curve to come up with the PT station. We did that by coming over here, it's PC station plus length. We had calculated or computed the length to be 416.66. So therefore our PT station is going to be 18 plus 92.26 or 1892.26. That is the station of the PT, and that's where we left off at our last set of slides. I am going to now go on and explain to you the items F through J here. Now, these are a little bit cumbersome and a little bit maybe intimidating in what exactly they are and how they actually help us in the solution of this curve. So this process right here from F through J is using some of the computation, some of the data here and some of the formulas that we have here to compute points that are specific along the curve. In this particular area, we're talking about F would be the very first deflection angle. What the objective of this would be to find a point along this curve at which we could begin to lay this curve out. Now, when I use the term lay this curve out, I'm meaning that what we would have to do to provide the builder with specific locations along this curve, we would have to set those in the field, and then the builder would then build from our data. This process helps us calculate where we would put those based upon the pieces of information we have in the field. So the first deflection angle is actually taking and imagine if we were to set our surveying instrument up and we had the ability to measure angles and take distances from this point. If we were to set our surveying instrument up here at the PC, we were to look at the PI station, have 0 in our instrument. The first deflection would be the angle that deflects off here and intersects this first point along the curve. The second piece of data, G here, which is a 25-foot deflection angle, that would be what the deflection angle is for every 25 foot along the curvature here as we move along. The next one, point H, is the very last deflection angle. What the last deflection angle is the data that would be, or the angle that would be required to turn from this line all the way through and actually get to our very last point, or the PT station. So it would be a matter of calculating that point right there. That is what is defined as the last deflection angle. Then items I and J here, the chord length for a 25-foot piece of arc length would be what is the straight line distance between the 25-foot pieces along the curve. As one would imagine, this is the arc length is along the curve, so therefore the chord length, imagine the term chord, stretching a chord tight, what would be the straight line distance between those? And then the last one, item J there, is the long chord, which would be the distance in this particular one, the overall long chord, which would be the distance from the PC station or where the instrument is setting all the way to the PT station. So if you'll bear with me, I'm going to switch screens here and go to our next screen, which is the whiteboard, and I will be using the whiteboard to make these solutions. Again, I apologize for my sketching here is it's a little difficult to do this given the drawing tools that I do have here. I'm going to start out by trying to replicate this again. So I'm going to go into the draw package here, and I am going to draw the curve coming in. As we again remember, this is our PI or our PI point right here. We know that we have a tangent distance coming down here, which is going to define our PC. And then we have that similar distance along here, or that same distance along there, which is going to be the PT. So again, remember this point is our PC, our PI, our PT. Our PC station, if you remember, according to our information, is going to be, let's see, it's going to be 14 plus 75, 60. So that would be this. I'm going to try to deal with my text editor here. So please be patient with me here a little bit. But it's going to be 14 plus 75.6 is equal to the PC. Over here, we have the PI station, which was given to us in the original set of data, which is 16 plus 9450, 94.5. And that is equal to the PI station. And then over here we have the PT station, which we calculated to be 18 plus 18 plus, oh, let's see, plus 92, 26. And in our last video, we actually came up with those locations or those measurements. So you can please revert back to the previous video to see how we do that. So now I'm going to come back in and say, okay, remember what we did, or our intention here was to use this to actually compute the curve data as it comes in right there. Let's see, I'm going to erase that and make that probably a little bit better. Let me try to get a better attempt at that. Okay, so there is our curve data. By the way, I'm using my finger to draw on the screen, so that might be a little bit reason for my shakiness as we speak. Oh, I noticed my PI station did go along there. I did lose that there, so let me go back to my PI station here again, and that was PI equal, or I'm sorry, not PI, but the PC station. PC equal is equal to 14 plus 75, 60. Okay, so the objective now is to set up our instrument right here at the PC point. So I'll go ahead and I'll draw in a little instrument there so we can see our instrument. Our instrument is now set up right here. We are backsighting this point right here, and we have 0 in the instrument. And the first thing I would like to do is calculate a point so that I could lay out a point along the curve. This is a point that's not on the tangent, but along the curve. What I would like to do is maybe define a point, say something there, and maybe a point here, and maybe some points along the curve here as we went along, and we would define those for the builder. Now, if we could define those points, that would be one of the best ways to actually find those points in the field. And then if the builder had those stakes in the field, then we could build either right or left based upon that center line of construction. So the handout that I'd given you actually takes into consideration, we take the data that we have, and we're going to calculate the very first deflection angle. So what is our first deflection angle? Well, my first deflection angle would be, at what interval would we like to go along this curve so that we could give the builder those particular control stakes? It looks as though, given the data that we've been given here, and this would be a communication thing you would do in the field with your contractor. But I would look over there, and you notice that in this particular station, the builder wants 25-foot intervals along the way. So it would be in my best interest to do even 25-foot intervals. So what I would like to do is get to station 15 plus 00 first. So I'd like to put station 15 plus 00. And then from there, I'd like to do station 15 plus 25, station plus 1550, station plus 1575, station plus 16 plus 00, 16 plus 25, 16 plus 50, 16 plus 75, et cetera, all the way along, and so that I could have even 25-foot intervals till I got to the end of the project here. Okay, I'm going to start out by, if you look at the formula of the data it was given, the first deflection angle was to find the length of the arc and divide it by the radius. Well, what is the length of the arc? Well, the length of the arc is going to be station 15. Oh, let's see, erase over here. Station 15 plus 00. And we're going to take off the 1475, 60. That difference becomes 24, 4. So in the formula, what we would do is the length of our first arc would be 24.4 divided by our radius. Our radius was given in our data, 550. And then we multiply that multiplied by 1718.87. Now, many of you may question, what is the 1718.87? 1718.87 would be our solution in minutes. So therefore, knowing that we wanted to actually lay this out in degrees, not minutes, the next thing I would do is divide the entire equation by 60. I know that does not show that on your handout, but it's just a step that would eliminate future problems for you all. So if you take the 24.4, divide it by 550, multiply times 1718.87, and divide by 60, you will come out with 1 point something with the decimal. What you would want to do then is convert that decimal back to degrees, minutes, and seconds. And our first deflection would be 1 degree, 16 minutes, and 15 seconds. Okay, so that being said, I'm going to go ahead, and that would be our answer for letter F. I'm going to go through and erase now. Hopefully you all had a chance to write those down. But let me go through and erase this information here. And I'm going to explain to you what actually we just calculated. Okay, so our objective was to get to station 15 plus 00. So what we have just calculated would be, and I'm not quite sure graphically where station 15 plus 00 is, but for ease in my drawing, I'm going to say, let's imagine that it was right there. This is station 15 plus 00. So what I have just defined would be the angular measurement. Let's see, very difficult to do in this situation, would be the angular measurement from here to here. So that angle, 1 degree, 16 minutes, 1 degree, 16 minutes and 15 seconds would be the angle that's formed if I had my instrument here, looking here, and turning that angle down to this point right here. That is 1 degree, 16 minutes, 15 seconds. I'm going to jump ahead down from point F now to point H, and point, I'm sorry, not point H, but it's the chord length, and actually I guess it's not asking us for the chord length there, but I would want to then calculate the length that I would then pull to get this particular distance in. If you notice the equations that show up for length, the equations for length, and that's length I and J, or points I and J in the data set. If you look at the formulas have some consistency in there if you look at them. And basically what it's saying is that for the first one, which would be the chord length for the 25-foot arc, it says that the formula is the sine of 25, the 25-foot deflection, times the diameter. And then the long chord is the sine of the total deflection divided by 2 times the diameter. So if you look at the equation, it's basically taking the sine of an angle and multiplying it times the diameter. So using that analogy, I am going to come over here and I'm going to calculate the distance from here to here. I have the angle right here, which is formed in our in item F there. The distance now is going to be using that equation, the equations that are generated in equations I and J. That equation is going to be the first length. So I'm going to say the length to station, and I guess, and I want to make sure that I define that this is a straight line length, not along the curve, but it is going to be the sine of the angle. And in this situation, I'm going to take the angle that I just got, which is the 1 degree, 16 minutes, 15 seconds. And if I divide that and I take the sine function of that, and then I multiply that times the diameter. Remember, the diameter is 550, which is the radius, multiplied by 2. If I take that formula, so it's sine of 1 degree, 16 minutes, 15 seconds, multiplied times 550 times 2, or 1100 if you want to do it that way. The length of that first arc is going to be, let me follow up with my calculator so we can go ahead and do that. 1 degree, 16 minutes, 15 seconds. Again, remember, you must convert that to decimal degrees. Take the sine function of that, multiply that times the 550, and then multiply that times 2. And we would end up with 24.39. So therefore, the first straight line distance is 24.39. So what we have just calculated is the angular measurement for point number 15 plus 00, and the straight line distance to get there. That is the process called deflection angles. I will leave the remainder of this sheet for you all to work out on your own, and get back with me should you have any questions. So this is the process for laying out deflection angles along a curve. Thank you. This ends video 3 on horizontal curves, and be looking for my next video series. Thank you. Have a good day. I hope you're staying safe. and I look forward to seeing you at talking with you all at our next session. And I am going to